Here's 2.4, part 3. Definition of a complex conjugate. When you have conjugates, the sign changes in front of the imaginary part. So my conjugates are my red and blue in this definition. If I have A plus BI, then the conjugate would be A minus BI. So if we give you a question like this, give the complex conjugate of 3 plus 5i, and there's a blank. Tell me what the blank is. What is the complex conjugate of 3 plus 5i? 3 minus 5i, yep. And then the next question, you don't need to write down. What happens when you FOIL complex conjugates? Does anyone know off the top of their head? What do I get as a final answer? What happens to some terms when I multiply by some things cancel out, some big players, yep. So I'm just going to show you what happens. You don't need to write that down. So if I take 3 plus 5i times 3 minus 5i, and I FOIL, I get 9, negative 15i, plus 15i, and then negative 25i squared. Those middle terms will always cancel out. What happens to my I squared off to the right? That drops and switches signs to a positive 25, and then I get 34. So when I multiply by complex conjugates, I get a real number. Imaginary numbers drop out. All right, that's what's leading us to this question. When we divide complex numbers, we could not leave an answer in standard form if we have an imaginary number in its denominator. It's not considered proper. So what you do is you look at the denominator and you multiply the numerator and the denominator by the conjugate. We do the same thing when we're working with radicals. It's not considered proper math to have a radical in the denominator. So we multiply the numerator and the denominator by the complex conjugate of that radical. So we'll do this example together. So we have 3 plus I over 3 minus I. What is the complex conjugate of its denominator? 3 plus I, we're changing the sign of that. So we're going to multiply the numerator and the denominator by the complex conjugate of its denominator. So now what we have to do is we have to do some FOILing. So I'm going to add some parentheses here. So I'll give you about a 1 minute lead time. Go ahead and multiply that. And remember, there's a shortcut to FOILing complex conjugates. All right, let's check. So, FOILing 9 plus 3i plus 3i plus I squared. Then the denominator. Do I need the middle terms in the denominator? No, we already talked about those cancel out. So 9 and negative I squared. First and last is all we need on that. Now let's reduce. Combine like terms in the numerator. 6i. What do I replace I squared with? -1. Denominator. What do I replace negative I squared with? -1, yep. Now I combine like terms again. 9 minus 1 is 8 plus 6i. 9 minus 1 is 9 plus 1, or 10. Now we can break up that fraction into two fractions. So I have my real part plus my imaginary part. And then I have a fraction I can reduce with the real to 4/5 and 3/5. And there's my final answer. Last example. We want to find the complex zeros of this function. We focused a lot in the first part of chapter 2 where we want to find the zeros of the function so we can find those x-intercepts of our graph. So if it was a cubic function, we could find up to 3 zeros, which could be up to 3 x-intercepts. If it was a quadratic, like the case here, how many zeros could I have? 2, because my degree is 2. So I can have up to 2 zeros or 2 x-intercepts. So we're going to find the zeros of this function. And the hint is, either try and factor it, in this case we'd have to use the AC method, or use the quadratic formula. Most students tend to not want to do completing the square, and solve by undoing doesn't work. So we're going to set the function equal to 0, and then solve for x. I'm going to go ahead and use the quadratic formula. So in the quadratic formula, identify your a, b, and c. Hopefully at this point you guys are probably rock stars at doing the quadratic formula, and you have that memorized. And now we substitute those 3 values in the quadratic formula. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And now we have some reducing to do. Be careful on your signs on this problem. Negative, negative turns that to a positive 1. And then negative, negative turns it to a positive 1. And then -4 times 2 is -8, times 3 is -24 over 4. Now we simplify underneath the radical, which is the radicand. 1 minus 24 is -23. What popped up in our simplifying? What's so important that just showed up? A negative square root. So we don't want to leave the answer like that. So we rewrite it as 1 plus or minus I, and square root of 23. Can't break down 23. And then 4s. When you get an imaginary number, so this is what we call a complex zero. If I go out and graph this parabola, imagine this parabola being above the x-axis. These are called complex zeros. They're not going to be x-intercepts. So no x-intercepts exist. So if I just think about the x-axis, I don't know what exactly it looks like, but this does not touch. That's what we call a discriminant. When the discriminant is a negative, that means there's no real zeros. They're called complex zeros. Is that pronounced too a little bit? This is called the discriminant. So no x-intercepts exist when you have complex zeros. Here's your assignment for today. 2.4, page 148. 3 to 81 multiples of 3. So you would do 3, 6, 9, 12, etc. I also passed out a review worksheet for you today. You don't have to start working on it until Friday, but some students like to work ahead, so they maybe don't have this homework over the weekend. Our next test will be on Tuesday. I will be collecting this assignment to grade on Thursday of this week. So I'm going to be a little stricter this trimester in getting homework turned in so students stay on top of it, because this trimester is more difficult than first trimester. Because after this, we're going to start getting into trigonometry, and you have to stay on top of your homework. You're going to see more time being spent in this class than you might have spent on in trimester 1.